Okay, so this is me in my new incarnation as director of Nordita, and what you don't see are the buildings next to me. I work in a former hospital building. So these were for infectious diseases that had to be outside of Stockholm because they were infectious. So I work in leprosy. Then we also have typhus, and we just got typhoid. Okay, getting serious. Cosmology started, well, let's back up. In antiquity, people wanted to know, what is the universe made of? How did it begin? And what is so cool is that in the last 100 years, we've made actually a lot of progress. We're really getting somewhere with these questions. And that all started with Einstein in 1915. He wrote down general relativity. And then other people applied those ideas, those equations, to the universe as a whole. And they realized that the universe could be expanding, it could be contracting, it could be static. In order to do that, they postulated some symmetries, that the universe is homogeneous. It's very smooth on large scales. Now, Einstein wanted more symmetry. He wanted a static universe so that it would look the same, not just at every point, but also at all times. Well, that didn't last very long, because in 1929, Edwin Hubble showed that the universe is expanding. So he was working in the Mount Wilson Observatory above Pasadena, and he made an astonishing discovery. He looked at galaxies at different distances from us, and you know what kind of light is coming out of the atoms, and he noticed that that light was shifted. The wavelength started out with one length that we know, but then by the time it got to us, the wavelength was longer. So what that means is that something is stretching the light that's coming to us. And the answer is the expansion of the universe. So at that point, Einstein had to admit that he had to abandon the static universe, because the universe is expanding. So if you wanted to have a picture, you might have something like this, where all the galaxies, every galaxy is moving away from every other galaxy. Now, Hubble never got a Nobel Prize, but he did get a postage stamp. So here's how we think the universe began, at least as far back as we know, and that was 14 billion years ago. The universe started out as a primordial soup. It contained all kinds of particles, quarks, leptons, photons, bosons. All of these things were very, very tightly packed together. But then as time went on, the universe started to expand. It started out very hot and very dense, but as time went on, it cooled and expanded. Sometimes we use a raisin bread model to show this. Imagine, hey, you guys actually know how to cook. So you may have seen this happen. You start with some dough and with a bunch of raisins in there, and then as it comes out of the oven, it expands. And so the raisins are moving apart from one another, not because they're running, but because what's underneath them is expanding. And that's a pretty good model for what's going on in the universe. Well, there's one major difference, though, and that is that the raisin bread has a central point. The universe doesn't. That's one of the symmetries I was talking about. If we moved, instead of being at our galaxy, we moved to a different one, you'd still see exactly the same thing. You'd see other galaxies moving away from you, no matter what galaxy you're sitting on. I wanted to say more about this concept of the Big Bang, because people, on the whole, have the wrong idea. Let's go backwards in time. Let's go from where we are now and take everything and bring it closer and closer together as we go backwards in time. Well, what do we get? Everything in this room would collapse to a point. But what about the stuff that's out at infinity? Well, as you go backwards in time, then sure, things getting closer, but guess what? They're still out at infinity. There's still something way out there. So no, the universe did not start from a point. It could have been infinite to begin with, and then just stretched or expanded as time went on. Well, what happens when you go backwards in time is eventually things are so tightly packed together that we lose our description in terms of physics as we know it today. You'd have to have a theory of quantum mechanics and relativity together that we don't really have yet. We have an approach that is the most promising is string theory. But so when we talk about the Big Bang, we're really talking about the limits of our understanding. So the Big Bang really was not an explosion, but if you did want to have one, please put one at every point. Well, now I want to turn to the question that I work on, which is, it's a really big one. What is the universe made of? If we take all the things in our ordinary experience, your bodies, the air you're breathing, the chairs or the floor that you're sitting on, the walls of this room, throw in the stars, throw in the planets, throw in all of that stuff. All of that is made of atoms, but all of that atomic matter still adds up to only 5% of the universe. It's the rest that we're left trying to figure out. So 5% of the universe is ordinary matter. Around 25% is dark matter, and the rest is dark energy. So what is this dark stuff? Well, before I turn to that question, let me just show you a recipe for the cosmos, the cosmic cocktail. So I wrote a book called The Cosmic Cocktail, and it's a popular level, and we were supposed to have some here, but something went wrong, so you can get them later, I hope. But anyhow, so in the book I put here, let's say you have I know you don't think in ounces, but let's do it anyway. So let's say you have a roughly 10-ounce drink. Well, then 3 ounces would be dark matter, 7 would be dark energy, and then you have a bunch of other stuff, including a little bit of a millionth of an ounce supermassive black holes. In the early universe, all of this stuff, better to think of it as shaken rather than stirred. And the secret ingredient is the dark matter that I'm talking about today. Well, to start the discussion about dark matter, let's talk about where it is and how we know about it. A good place to think about this is our Milky Way galaxy. At the center of the Milky Way, it's shown in yellow, but it's not yellow, but there's a giant black hole. It weighs about 4 million times as much as the sun. And then you have these spiral arms of structure, like a pinwheel. So I guess that pointer still isn't working, huh? Okay, so anyway, so here, these are the spiral arms of structure, and you can see the sun up there along one of those arms, and that's where all the stars are, pretty much anyhow. When you look out in the night sky and people say, oh, look at the Milky Way, then they're talking about the stars, which is actually only a small part of the whole picture, because now let's go look at it from the side. And all of that is in a flat plane. Out from the center, this distance to the sun is about 25,000 light years. But all of that, we call it the disk of the galaxy. That's only a small part of the whole thing. And in fact, most of the mass is in a giant spherical region that we call the halo of dark matter. This is an artist's representation, where you see the spiral galaxy, and then the dark matter that is everywhere. Well, that's kind of where the dark matter is located, is inside galaxies and structures like that, but I want to tell you how we know that. So so in order to do that, I'm going to make a comparison with the solar system. So for a moment, I'm not talking about galaxies, I'm not talking about dark matter, I'm talking about an analogy that's useful to explain how we came to understand the existence of dark matter. Okay, so let's look at the average speeds of planets in the solar system, starting from the sun at 0. When we move out to the right, then we're looking at planets farther and farther away from the center. So the first one, Mercury, is the fastest, then Venus, then Earth, and as you move out, they get slower. It takes them longer to go around. If you want to put it in terms of an equation, the speed is determined by, well, the distance from the center, but also the mass of the sun. So if I had a sun that was 4 times as massive, everything would be moving twice as fast. So mass is determining speed. Well, I have to tell the story about Tycho Brahe. He's the man who studied these planetary orbits, and I guess he was a character. He lost his nose in a duel, and then wore a gold and silver replacement. Oh, and this was a story for you guys, because this is about Denmark. So he was at dinner with the king, and he was supposed to, you weren't supposed to get up until the king did, but Tycho Brahe drank too much wine. His bladder burst, because he couldn't go to the bathroom, because the king was still sitting. and 3 days later he died. Now, there was a competing theory, which was mercury poisoning. Okay.
The red one.
I can't see.
That's you.
This one?
Yeah.
Well, I don't want to kill somebody, blind somebody. Okay, so anyway, so there's a competing theory for his death, which was that there was mercury poisoning because his most famous student, Kepler, wanted Kepler's laws named after himself. So believe it or not, they actually, I don't know if it was about 15 years ago, they dug up his body here in Copenhagen, and they did an analysis of his mustache hairs, and no, there's no mercury poisoning. But isn't that cool? They actually dug him up. Anyway, so I guess, I guess he just had too much wine. The theme of his talk, cocktails, right? And you're having them. I don't get any till I'm done, but anyway. All right, so that was the rotation curve of the solar system. Now let's go back to galaxies. So instead of the solar system, I have at the center of the galaxy, I look at something moving around the galaxy, and the speed of whatever this is, gas or stars or whatever, the speed is determined by the amount of mass in the interior. So if you have things moving very, very rapidly, then that tells you that you have more mass in there than you thought. And that's exactly what happens. So this dates back to 1933, the work of Fritz Zwicky, who was also using the same telescope that Hubble did, actually. And what he looked at the Coma cluster. This is a cluster containing hundreds of galaxies. And he noticed that some of those galaxies were moving too rapidly based on the stellar material that he knew about. Something was pulling those galaxies and speeding them up. He proposed dunkle Materie, which is the German for dark matter, as the explanation. So when he said dark, he just meant it doesn't shine. It's not stars, it's not giving off light that he could see. And that was actually the beginning of the dark matter problem, all the way back to 1933. Now he was I don't know what kind of person he was, but I do know that in his book, he called his colleagues spherical bastards, because no matter what direction you look at them from, they're still bastards. Now, I did a radio show that runs from 2 a.m. to 5 a.m., okay, in the U.S., and this woman called in, his daughter, and guess what her name is? Barbarella Zwicky. Now, if you haven't seen the movie Barbarella, you got to do it, okay? It's a hysterical movie. But anyway, so she was complaining that nobody listened to him at the time, and she's writing a book about the history. And I hadn't really appreciated that people didn't believe he was right about this. So it wasn't until 4 decades later, it was the work of Vera Rubin in the 1970s, and that's what convinced people that dark matter really has to be there. So she found dark matter in every single galaxy she looked at. And that's what it took to get consensus in the scientific community that dark matter has to exist. So for the life of me, I don't understand why she hasn't won a Nobel Prize, and she's in her 80s, so I hope they hurry up. I really mean that. There have been like, what, 2 women who got PhDs, who got Nobel Prizes, and I guess I'm one of them, right? Anyway, she should get one, a Nobel Prize. She has a PhD, okay. So she studied rotation curves of galaxies, and here's what she saw. So if it was like the solar system, you'd expect speeds to drop off as you move away. In this case, you're moving out from the center of the galaxy, and this is what you'd expect based on the stellar material, the stellar mass you know about. But instead, this is how things are moving. They're moving very, very fast. So again, something's speeding them up, and if you add in the halo of dark matter, then it all works out. And let me remind you, the halo is this big spherical object that contains the dark matter. Well, that was the original way we knew about dark matter, but since then there's been so many observations that point to the same thing. Another one of them is Einstein's lensing. This is a great way to look for mass in the universe. Whatever that mass is, this black thing here, if you have some star you're looking at in the distance, then the mass bends the light. That's Einstein's lensing. So not only does it bend it in one way, but it might bend it the other way, so that you end up with what you actually see are these things, and you end up with double images. So there's multiple images, they're sheared, they're funny looking, and kind of like my graduate student, as he gets more and more lensed. Now here's some real data from Hubble Space Telescope, and in here there are multiple lensing objects. And so you have some distant background light that is bent, sheared, you have multiple images and so forth, and with the computer you can now reconstruct what is the mass in between your distant bright objects and you and your telescope. And when you do that, you get things like this. Not the same object, but it's the same type of thing. Also data from Hubble Space Telescope that you use the computer to reconstruct what the mass is, and you have, this is a cluster. You have hundreds of galaxies showing up, the mass of the galaxies, but you also have this smooth component underneath, which is the dark matter, in this case, in between galaxies, inside the cluster. So this is the kind of stuff that Fritz Zwicky was first identifying. I want to show you one more picture, because this is a beautiful piece of evidence for the existence of dark matter. It's called the bullet cluster because I guess it looks like a bullet. Somebody thought so anyway. And what you see here is a distinction between two different types of matter. On the one hand, you've got, this is just shown in pink. It's not pink, of course, but this is the atomic matter. What happened was two clusters of galaxies hit they hit one another, and eventually they'll merge into a single galaxy. But what happens when they first hit is that the atoms get stuck. Atoms have electromagnetic interactions. They have strong interactions, which is what holds your nuclei together. So if one of you, if you or I if we hit each other, we would get stuck. We wouldn't get very far because we have a lot of forces, interactions between us. So that's actually observed in terms of by X-rays that are emitted by gas. The dark matter, on the other hand, that dark matter goes right on through. It does not have electromagnetic interactions. It does not have strong interactions. Yes, it feels gravity, so eventually it'll come back. But on the first go-round, this mass, which was seen by lensing, shown in blue, has a clear distinction. It behaves differently than the stuff that's in pink. So you have two different types of material here, the regular matter and the dark matter. So most of the mass in galaxies and clusters of galaxies, more than 95%, is made of dark matter. And I've shown you some of the evidence for that. And I want to show you one more thing about evidence for dark matter. This is interesting. We actually would not be able to exist without dark matter. Now the reason for that is the formation of galaxies wouldn't have happened quickly enough. Regular matter talks to photons, it interacts with photons, particles of light, and they stream out. So let's say you're trying to collect matter into a galaxy. Well, it doesn't work because the photons move out and they pull the mass out with them. But dark matter doesn't interact with photons at all. That's why it's dark. That's why you can't see it. So dark matter is able to clump, and it does it, well, in a way that I'm going to show you with simulations, but basically what we need is the dark matter to make the galaxies, and then the atoms fall into the galaxies, and then we can come into existence. So this is done on a computer. You start out with dark matter particles. They're almost entirely uniformly distributed, but there's some clumping, a little bit of clumping that started at an early period of the universe called inflation. And this up here tells you how dense the universe was. So length scales were 30 times more tightly packed than they are now. And what happens is the dark matter is shown in terms of blue objects. I don't know why, but anyway, so what happens is that this almost uniformly spread out stuff is going to clump together and make structures. So we can watch this happen as time goes on. You can see that blue stuff collecting. And then here we have the universe today, according to this computer simulation. You have these long strings of mass, and at the intersections, at the nodes, is where you have the galaxies. And this computer simulation really matches reality very well. So this is how we think structure formed in the universe. So So I've told you arguments for why we believe dark matter exists and its role in structure formation, but then there's the big question, what is it? It's this big chunk, 25% of the universe. Now the first thing you might try would be rocks or gas or dust or snowballs of hydrogen or some simple things like that, but almost very quickly it became clear that they're impossible because they would have had observational signatures that we just don't see, so it's not right. So even 15 years ago, there were still two camps. There were the people that believed in the MACHOS and the people that believed in the WIMPs. Okay, so MACHOS are massive, compact halo objects. These are objects, they would have been made of ordinary matter, but even then people were speculating that you had to have something non-atomic, and that was driving people to look at exotic candidates, such as WIMPs or axions or other particles. I played a role in both sides of this debate. So on the MACHO side, the types of objects these could be would be faint stars or planetary objects. The stuff was dark, but that could be because we didn't have good enough telescopes to find it, and if you just get more sensitive, then you'll be able to find the dark matter. So that was a possibility. But we showed that actually these two can only be about 3% of the galaxy, using a combination of data from Hubble Space Telescope and also some theory. What about stellar remnants, white dwarfs, and neutron stars? When stars run out of fuel, they will collapse down to very dense objects, and so it was possible that you would have a lot of that. Now, it turns out that it's still true. White dwarfs could be 15% of the dark matter, but they can't solve the problem entirely. So, in short, baryonic, that's the atomic dark matter, is not enough. Okay, so I have nothing to add on that, on this. The head of the CERN theory group, this was a while ago, came up to me afterwards and said, "I'm a WIMP." Yeah, and I said, "Yeah, and you're a married WIMP." I actually didn't say that, but in retrospect, I should have. But anyway. Okay, so what do we think is going on here with the dark matter? Well, we think it's some new kind of fundamental particle, not neutrons, not protons, something new. And my friend said to say, wow. Okay, so candidates. Well, there are a lot of them. I'm not going to talk about most of them, but neutrinos is how sad that they don't work. They're too light. They contribute 0.5% of the mass of the universe, so they don't do it. They exist. That would have been so great. But no, we have to go outside. So of all these at the top, and I'm going to talk, for the rest of today, I'm going to talk about the WIMPs. I want to tell you why, they, in my opinion, and the opinion of many others in my field, they're the best candidates. So what does the name mean? Well, the WI stands for weakly interacting. And you remember I said the dark matter does not have strong nuclear forces, does not have electromagnetic forces. Well, there's only one more fundamental force, and that is something we call the weak interactions, which is also responsible for some types of radioactivity. So I will tell you that billions of these particles pass through your body every second, but you don't notice because they're not interacting very often, maybe once a month with one of your nuclei, and it doesn't do anything. You know, I used to think it was once every 100 years and it's what killed you, but it turns out it's roughly one a day or one a month, so there goes that theory. Anyway. So so the rest of the name, the M for the massive, what we mean by that is it weighs 1 to 10,000 times as much as a proton. Okay, so why do we think they're such great candidates? There's two reasons. One of them is that these things are their own antimatter. That means whenever two of them encounter one another, they annihilate and turn into something else. So the original WIMPs are gone, they've turned into something else. Well, in the hot early universe, all particles were interacting with each other all the time, and including a lot of this annihilation was going on. We can do the math, we can do the calculations, we can tell you how many there were at different epochs in the universe. And the annihilation doesn't happen forever. Eventually, the universe expands to the point where particles don't find each other anymore and the annihilation stops, and we can tell you how many are left. And that calculation comes out really beautifully. In the end, you get the right amount of dark matter and the only postulate we've made is that these particles have these weak interactions. So some people call that the WIMP miracle. Sometimes some people say, oh, come on, it's just a coincidence. But anyway, that's why we take WIMP so seriously. But there's a second reason, which is that in particle physics, there's a lot of unsolved problems. And in people who are working on those theories, in the solutions they come up with, you automatically have particles sitting inside those theories that really have nothing to do with, well, you get dark matter out automatically. You get WIMPs automatically. You didn't put them into the theories. They come out of the theories. So that's a byproduct of theories that existed for other reasons. And one of these is supersymmetry. Supersymmetry is an important extension of the standard model of particle physics. If it's right, then every particle that we know about has a new partner, a new heavier partner. For example, you have the quarks. Having a new partner is called squarks, and you put a twiddle over the top. Or the photon as a new partner, the photino. Now, all of these particles are unstable in that they decay to ever lighter and lighter, lighter particles until you get to the lightest supersymmetric particle, and that thing is stable, and that thing is a WIMP. It's a perfect WIMP candidate. So when people write down supersymmetry models, they're not doing it to try to solve the dark matter problem, but you automatically get a dark matter candidate out of those theories. Well, that's all well and good. We have a nice model theoretically, but we're not done until we find the damn thing. So, three-pronged approach to WIMP detection. And here's where I have the too many slides that you were so worried about. But I'll tell you something about each of these, a little bit about each of these approaches. It's really the same diagram I've got, but you look at it in three different ways. And the first one is you have protons colliding together, and that would happen in accelerators, in particle accelerators. And then you would make the dark matter. Chi, by the way, is a Greek symbol that we use for the dark matter. So you could create the dark matter, and that would happen at accelerators. Or you could scatter the protons, the WIMPs could scatter off of protons that are inside your detector, and you detect that. That's called direct detection. The third approach is that you look for WIMP annihilation in particular regions of the universe today, and you look for the stuff that comes out. Indirect detection. So let me get back to all three of these in more detail, starting with the colliders. So in Switzerland, in Geneva, there is the CERN accelerator facility, and the Large Hadron Collider is this thing. It's 27 kilometers in circumference, and you have two proton beams. They make collisions at 4 different places with detectors at those 4 places. I have to show you some pictures. So this is the Atlas detector. There it is, with Fabiola Gianotti. She's now the Director General of CERN. Okay, another picture. Here it is again, the Atlas detector, and there's somebody standing there just to give you a sense of scale. Thousands of people it takes, thousands of physicists and technical people and so on to build these giant things, and it's the biggest computer project in the world too. Here's the other detector, the general purpose detector CMS during construction. I think these are beautiful things. Okay, this is a detour, but I have to do it. So you have in this is an image of an actual collision of a proton coming in from the, ooh, I guess I hit something. Let's try that again. Okay, so proton from the left, proton from the right, they collide, a bunch of stuff happens and then it decays and da-da-da-da-da. This is a real image, well, it's a computer reconstruction, a real event that happened at CERN that was, this is a Higgs particle, the discovery of the Higgs boson, the last missing piece in the standard model of particle physics. So you make a Higgs, it doesn't last very long, and it decays into other things. And you can reconstruct every step of the way of every one of these decay particles in these detectors and extrapolate back and ask what happened. And there's this bump here that tells you that GeV is basically a proton mass, that at 125 proton masses, something happened. That's the discovery of the Higgs boson. And 2 of the 6 people who first proposed it in the 60s got the Nobel Prize immediately. Now, Higgs bosons are not the dark matter. They decay very quickly in about 10 to the minus 22 seconds. The dark matter, well, our universe is 14 billion years, so that's not the answer. But this has been a major, this is the big success that's come out of the LHC so far. Now, the other big thing they're looking for is supersymmetry and dark matter. So that's the next big goal that they have. And they're going to turn on again in a couple weeks. And let's hope they find it. Second way to search for WIMPs, underground laboratory experiments called direct detection. All right, there's my nucleus that makes up my detector. Remember, we have these WIMPs flying everywhere around in the galaxy, tons of them, billions going through you every second. Every once in a while, one of these WIMPs will scatter off of the nucleus of the detector and leave a little bit of energy, and you can detect that energy deposit. Expected rates less than 1 count per kilogram of detector per day. These are very difficult experiments. Okay, it takes me back to cocktails. This is how did I get into dark matter? Well, I was at a winter school in Jerusalem, and I met this man, eccentric, genius, speaks English, French, German, Polish, all at the same time. And he knew where to go for the New Year's parties, okay? So while we were there, while we were drinking, whatever, he starts telling me about work that he had been doing with Leo Sadolsky, his collaborator in Munich, on ideas they had for neutrino detection. Now, neutrinos are a lot lighter than WIMPs, but they are also weakly interacting particles. So the techniques they came up with, you should be able to use for WIMPs. So I was working at Harvard at the time, and we got him to come back to Harvard, and together with our third collaborator, David Spergel, we did we did calculations. We put in we thought about what kind of behavior the WIMPs have inside the galaxy, and then did some calculations of what kind of interactions they would have with the nuclei. And we showed that it was worth building these detectors, and that's what people started to do. So but one thing you have to do is go deep underground, like this mine in South Dakota, because you have to escape cosmic rays. Cosmic rays are going to swamp your signal. But if you go deep underground, only the WIMPs will get down there. So let me show you a picture of all the different experiments that are doing this now, all over the place, all over the world. I'm going to tell you a little more about in the Gran Sasso tunnel that's outside of Rome, some of the work that's being done there. So at this point, there are claims of WIMP detection, but the question is, are any of them right? But let me tell you about the one in the Gran Sasso tunnel. Okay, here's what they were looking for. They have crystals made of sodium iodide that they're deep underground, and they're waiting for the WIMPs to hit the crystals. But now I got to tell you something about the behavior of the WIMPs. Well, the sun is moving around the center of the galaxy, so I'm going to be the sun. I'm going to move around the center of the galaxy, and the WIMPs are coming at me on the average. So there's a wind that I'm moving into, a wind of WIMPs, and that's exactly what our detectors are doing. So you get a lot more counts in one direction. Well, and then the Earth goes around the sun, and that means that the count rate should peak in June, and it should be a minimum in December. The relative speed is a peak in June. What you'd expect is this behavior that is exactly what's seen by the experiment called DAMA, the Italian experiment in the Gran Sasso tunnel. They have 10 years worth of cycles, and they're exactly with the right phase. So, are we done? Did we solve the dark matter problem? Not yet. There's a couple of problems here. One is that they won't let anybody look at their data. This is the quote that they have on their webpage. It's from Rudyard Kipling. And I don't understand that. Nobody understands that. But the other problem is, comparison to other experiments, is that other experiments have null results. How do you reconcile positive and negative results? Well, before I go any further, I have to show you some of the people involved. So this is Juan Colliar, head of the Cogent experiment, Rita Bernabe, the PI from the principal investigator of the Dama experiment, and Elena Prelay of the Xenon experiment. And here's what he said to me. I'm a Spaniard caught between two Italian women. So we have conflict not just between the experiments, but between the experimentalists. Okay, so now if you want to compare Dama, which is made of sodium and iodine, versus, let's say, some of these experiments, xenon and lux, well, those are made of xenon. It's a different material. How can you compare this? Well, you have to put in some theory in order to put them on the same plot. So in this particular plot, what I've done is assume the scattering scales as atomic mass squared so that I can plot everything together. If I do that, then, this is WIMP mass. This is the strength of the interaction. To be compatible with Dama, you have to be in one of these orange regions. But to be compatible with the experiments made of xenon, you have to be below the red and purple regions. Does that mean lux and xenon rule out Dama? Well, no, because only if you make this theoretical assumption can I even plot them this way. So it's like comparing apples and oranges. It becomes tricky. Okay, just some fun pictures of meetings that we go to. This is the leader of the Lux experiment, so you ask yourself. That's a pretty, actually they make bigger margaritas at the Baja Cantina. But the thing you gotta do is take sodium iodide crystals somewhere else on the planet and do the same experiment. If you see it again at the South Pole, the same results at the South Pole, then you'll know, aha, then Dama was right. That's what's going on. So here's the top of the ice in the South Pole, and then there's an experiment called Ice Cube that has phototubes down to a kilometer beneath the ice. Those are actually looking for neutrinos, but what you can do is stick sodium iodide crystals alongside these phototubes and then see if you see the same results. At the South Pole, that's a very different environment than Rome, outside of Rome. So that's a good check. Now the only downside of being a theorist, I don't get to go to the South Pole. I get postcards from the South Pole. So I don't really, I have way too many slides here. I know you're right. But anyway, I do have to tell you about, this is our latest idea. This is also with André Druquier. And so the idea here is to not just count the particles that are hitting you, but also get the direction they're coming from, because then you really can understand what you're looking at. So the way we do this, we have a very thin plane of gold, nanometer thin, with, yes, these are strands of DNA hanging down. Huge numbers of them. So when the WIMP comes along, it knocks the gold nucleus forward into these hanging strands of DNA. I want to make sure that you know the WIMPs are not breaking DNA, but gold breaks the DNA. Now the beauty about DNA is you can control these strands. A, C, G, da-da-da-da-da, and so you know exactly the sequence. So when the gold breaks it and it knocks these strands down, you collect them and you can reconstruct this track with nanometer accuracy. That would be so awesome. And then because you've got this track, you can figure out where did the WIMP come from. You can check, do I have a WIMP wind in the right direction, all this kind of stuff, and then you'll really know what's going on. Well, we had the accelerators, we had underground labs, and the third way to look for these things is indirect detection, where you're looking for the annihilation. 2 WIMPs in any region where there's a lot of dark matter, and there are some regions like that still, will annihilate into other things and go through a chain, and at the end, the interesting one that we're going to talk about now is the gamma rays. These are very high energy photons that you can look for. So there is, in fact, a satellite out there called the Fermi satellite that is looking at the gamma ray sky and searching for gamma rays, particularly the thing I'm talking about, from dark matter annihilation. So my friend Doug Finkbeiner discovered this bizarre thing called the Fermi bubble. Here's the plane of the Milky Way, but then look at this, this is gamma rays, shown in purple, 50,000 light years in extent. Now, most of this is ordinary astrophysics, has nothing to do with dark matter, but there's a central region that could be from dark matter annihilation into gamma rays, and there's a lot of excitement. Maybe this is the discovery of dark matter. Well, we have several pieces of evidence for the dark matter now. I mentioned the Dama annual modulation. And then I mentioned the Fermi bubble near the galactic center. And now it's the job of the theorists to try to figure out what's going on. How do we reconcile the null results, the positive results, the different types of experiments? Could this be the same WIMPs in these two experiments? And I don't know the answer to that yet. Well, in the end, you have to have more than one experiment see the same thing. And not only that, but you have to have the people agree. Well, I can't resist talking about my baby, which is dark stars. You can see this as a fourth way to search for WIMPs. This is the idea that dark matter annihilation can power the first stars. Okay. I don't know if you've seen this movie. So the three of us, we had this idea in 2007. And the basic idea is that you've got a cloud of hydrogen when the universe is only 200 million years old, very early on. It's collapsing, but there's a lot of dark matter in there, and it eventually takes over. So the dark matter annihilates, and the annihilation products heat up this object. And yes, it's a star, and it can grow to be very large. The dark star, it's made of hydrogen, not much dark matter in there, but it can grow to be 1,000,000 times the mass of the sun and 1,000,000,000 times as bright. And although the Hubble Space Telescope can't see it, the next thing that is called the James Webb Space Telescope in 2018 could discover these. Okay, put your karma, give me some good karma here. Let's find it. Thank you. All right, so we have direct detection, indirect detection, collider searchers looking for dark stars, and the hope is that within the next decade we're going to nail this problem. Well, back to the pie chart of the universe, there's still this big elephant here. There's 70% of the universe that's called dark energy, and that's a much harder problem. Dark matter, we know this there, we know how it's distributed, we have good ideas for what it could be. Dark energy is really a mystery. The only thing we know about it is that it is causing the expansion of the universe to accelerate, which surprised the hell out of everybody. And then we're trying to figure out what it could be. So it's some kind of, matter accumulates gravitationally, but this stuff has the opposite behavior. It's kind of a repulsive force. So, and I don't have time to talk about it really, so I'll just tell a joke. All right, so I was on a panel in New York at the World Science Festival. This is me, Eleanor Aprile of the Xenon experiment, Glenys Farrar, who worked on the bullet cluster. We were talking about dark matter. Then over here you have Mike Turner, Saul Perlmutter, and Brian Greene. You may know his popular science books. They're the best. The three of them were talking about dark energy, and so I had so we're talking about dark matter. They're talking about dark energy, and so I made a true statement about the physics. Yeah, how could I resist? So anyhow, I was going to end with this picture because this is my book, The Cosmic Cocktail, 3 Parts Dark Matter, which we were supposed to have some copies here, but they didn't get here. But someday, go take a look if you want to learn this. If you want to read more about the kind of stuff I was talking about today. And thank you all for coming.